Good to go.
We want to start new stuff today. So we're moving on past heat and going into electricity. Thanks for cleaning the board.
Welcome.
All right, we want to start with Coulomb's law and the beginning of electricity. And Coulomb's law tells me how two charges interact. So I have a blue charge and a red charge. Yeah, traditionally the blues are negative and the reds are positive. So there's this force that exists, right, called the electric force. And it depends on the charge of the particle. And we have two charges, positive and negative. You want to figure that out? Great. The first American physicist. He was also a statesman.
Benjamin Franklin.
Benjamin Franklin with the kite, right? Nah, zapping. We figured out we had two charges. So, early American physics history there. So anyways, this is the idea. And you can see the force here. It depends on the size of the charges. So if I make the charge big, right, bigger, the force is going to get bigger. See that? And smaller. And what do you notice here on each of these particles? This is Newton's third law in effect. What?
Equal and opposite.
Equal and opposite forces, right? Charge 1 exerts a force on charge 2. Charge 2 exerts the equal and opposite force on charge 1. We can make them. What happens if they're both negative? They repel each other. Like charges attract, right? Nope. Like charges repel. Opposite charges repel. It's like a romantic comedy, right? You watch those. Rom-coms. I don't think they're as popular as they used to be. Back in the 90s, that was what you went and watched.
I think a lot of girls my age grew up on them.
Yeah.
Like not, and you don't watch them now to watch them. You watch them because they're
Nostalgic, right? That's what me and Mrs. Browning would go see movies. Because we were young and in love with it. All right, so that's the idea. It also depends on the distance. So notice if I move this guy away, what's happening to the charge? Right, when they're further apart, the charge is weak. And when I bring these people together, let's get them really close together. Notice the charge is not linearly increasing. It gets a lot bigger. Okay? The formula that describes this is called Coulomb's law. And the force is equal to a constant, another K, not the Boltzmann constant, it's the Coulomb constant. Can't help it, that's what it is. The product of the charges, Q1 and Q2, divided by the distance between them squared. So far this is all numbers, so that's a scalar, but it's a what? Force is a vector, so we need a vector part, which is r hat. It's the direction between the charges. Right?
What did you say K was again?
K is called the Coulomb's constant, named after Charles Coulomb, who discovered this law. Yes?
The Q's are the charges?
Yeah, the Q's are the charges. And you'll see capital Q and little q, both for charges. Usually capital Q is like for big charge, little Q is for like little charge. That's kind of the way we do it.
Do you know how to spell the
Coulomb?
Yeah.
I'm going to look it up right here in the book. C-O-U-L-O-M-B. Coulomb's law. That's Coulomb's constant. Interesting note. Coulomb has the same birthday as me.
What? Wait, when's your birthday?
June 14th.
Dang, we're like 8 days away.
You're close, huh?
Just like
Okay, you're close, but it's not Coulomb's birthday. So K equals 8.987. This thing is really measured. 551788. I can't believe they even have that many digits for it. We probably just need like 3. But I give it to you just for times 10 to the 9th. Newtons. Oh, this is, it keeps going. meters squared per Coulomb squared. Okay. That's Coulomb's constant. And he discovered this force. So if I have two charges, you can see the force gets bigger as they get closer together. It's a 1 over r squared relationship. So if I graph magnitude of force as a function of distance, right, it's a 1 over r squared law like that. So it's not a very big square. So it's very strong closer than it falls, right, as you get further apart.
Does C stand for coulombs? C. What C stands for?
There's no C.
Newton meter squared divided by C.
Oh yeah, C, you're right. Charge units. The units are coulombs. So yes, it does.
The coulombs are a unit of charge.
Coulombs are unit of charge. It's Coulomb's constant and it's Coulomb's law.
So those Q's are measured
And coulombs, yeah, that's what we measure charge in. Coulombs. Now in chemistry, you probably measure charge differently.
Am I allowed to forget like what every
Okay.
every letter meant in the last chapter?
Yeah.
Like, can we like?
Because Q is just like heat, right?
Yeah, Q is heat.
Yeah.
I mean, for this part, not forever.
Like for this unit.
For this unit, yeah,
For this course.
we're leaving heat behind.
Everything behind, like C is not so small.
Yeah, C.
No, C is not Celsius. C is Coulomb.
C's not so-
R is still distance,
That's good.
and F is force. So
That's like 2 out of like 5. Right?
yeah, so that's good. We got 2. Okay, so that's Coulomb's law, right? I mean, I guess we could try some problems. Right, it's a pretty simple law, but it's kind of messy because there's an r hat, 1 over r squared. Oh, another way to write this law, if you want it, is equivalent. Okay, q1, q2, r vector divided by r cubed. That's the same thing, right? Everybody see that? Because what's r vector over one of these r's? That's r hat. Right? Because I could write this as k q1, q2 over r squared, r vector over magnitude of r vector over magnitude of r is r hat. So you can write it either way, it's the same. We're going to do a lot with this, but let's just start with a problem. I think that's the way to go. So let me pull up the book. Let's see. No, I don't think I'm going to send it. Oh, maybe I don't. No, that doesn't work. Maybe I'm gonna
Dr. Johnny,
Yeah.
does the R in the module means that we have to take the module of a coordinate? Let's say we have an X and Y coordinate. We have to do the square root of
Yeah,
X
this is the magnitude of r, yep. So it's the distance squared. That's what that means.
magnitude.
We'll start with an easy one. So we are in chapter 19. And let's go to the problem. Open the plug. Okay, let's try this one. Let me get big. There it is. 2 identical conducting small spheres are placed with their centers 0.3 meters apart. One is given a charge of 12 Newton nanocoulombs, and the other a charge of negative 18 nanocoulombs. Find the electric force exerted by one sphere on the other. What if the spheres are conducted by conducting wire? Find the electric force each exerts on the other after they come to equilibrium. Okay, so in the first part they talked about conductors and insulators, so I should mention that quickly since that problem references it. Conductors allow charge to move freely, right, like a metal wire. That's why you plug into the outlet. And insulators It's not that they don't allow charge beyond them, but they don't allow charge to move. They hold charge in place. Okay, so you can have charge on an insulator. An example would be a balloon. You guys ever do that? You roll a balloon on your head when you're little. What happened?
Your hair sticks up.
Your hair sticks up, and then you can take that balloon and stick it to the wall. Anybody ever do that before? That balloon's an insulator. Rubber's an insulator. You're sticking charge on it. It's just not moving around. It's being held in place. So insulators hold charge in place. Conductors allow charge to move freely. So like, I have a plug, right? The inside is metal, because that's a conductor, and the outside is wrapped in rubber, which is an insulator. So it keeps the charge in the middle. Does that make sense to everybody? That's how that works. Okay? So when you have conductors, the charge will move and it'll spread out to equalize. It's kind of like thermal equilibrium, but we have electric equilibrium. The charges distribute themselves across a conductor. Okay, does that make sense? So you'll need that for part 2. So part A, find the electric force exerted by one sphere on the other. Part B, now you connect them by a wire so you can equal out the charge. What's going to happen? Well, positive charges are going to be attracted to negative charges, right? They're going to cancel out, and you're going to redistribute the charge that's left. So that's part B. So this one, you should be able to do that. Just plug and chug. Coulomb's law. All right, this one shouldn't be too bad. We'll get a little more interesting here in a minute. But just so you get a feel for the problem. And Jerry's got a calculator. Anybody else got a calculator? Sarah's got a calculator. He's got a calculator. We got a lot of calculators today. Mary, you got your calculator? You got a phone that works? We just plug in the numbers, right? This is pretty easy. Oh. What does nano mean? 10 to the negative 9, yeah. Usually you don't have a coulomb of charge. That's a lot of charge. So we're dealing with microcoulombs, nanocoulombs, things like that. Okay? So you're gonna have to get used to 10 to the negative 9, 10 to the negative 6, 10 to the negative 3.
Micro is 6.
Micro is 6.
And then
Nano is 9.
and then pico is 12.
Pico is 12. We usually don't have pico in this, but pico is 12. Negative 12. Alright, so we just find the electric force exerted by one sphere on the other. So that's easy, right? So here's Q1, here's Q2. The distance R is, I think, what? 0.3 meters? Just put in the numbers. Let's calculate the magnitude. So that's Coulomb's constant, 8.8 or 987. 988, right, if I round to 3 decimal points, times 10 to the 9th, times, now if I'm calculating the magnitude, let's calculate the whole vector. Let's not do the magnitude, the whole vector. So this is Q1, which is what? Make that one 12. And this one negative 18. Let's calculate the force on 1 on the 2. All right, does that make sense to everybody? So I'm going to calculate this one acting on that. So I got the Coulomb's charge, I need the charge. So 12 times 10 to the minus 9, negative 18 times 10 to the minus 9. The distance is 0.3 squared, and now I need the direction. What's the direction from 1 to 2? To the right, which is, remember these things? I hats, J hats, all that stuff.
Couldn't it be above? How do you know it's in the
I just picked to the right. So.
Oh.
Yes.
They're both like I hat, are they not?
Well, this one is negative I hat going that way,
Yeah.
and that makes a difference.
It could be J, right?
Right, if I put them above, it'd be J. They didn't tell me, so I just picked. So what do we get for a number here? Anybody? Jared, you got it for me?
Yeah, I'm not sure. 2.157 times 10 to the negative
2.517.
times 10 to the negative 5.
Right now, if I were to calculate the other way, what would be different? This is charge 1 acting on 2. If I wanted to calculate 2 acting on 1, what would be different?
Would be negative.
What would be negative? Sarah, what would be negative?
12.
You flip the final result. So
Yeah, but
instead
how do
of-
I get that? I still have 8.988 times 10 to the 9. I still have 12 times 10 to the negative 9. Still have negative 18 times 10 to the negative 9. I still have 0.3 squared. but
I
what
is
would
gonna be
different.
negative I.
Negative I hat because it would be going this way. You see that? And that should give me the equal but opposite negative 2.517. So in this formula, when I do it, I gotta keep track of charge signs and direction signs to get the total sign correct. Now, they probably just calculated magnitude. Yeah, they just did magnitude, 2.16. You got 2.517?
I said, maybe I said it wrong, I had 2.15.
Oh, maybe I heard you. So like, that's flipped. Mary.
Wait, so which one is negative and why?
If I go this way, it would be negative,
Okay.
right? If you think about it, this one's positive and this one's negative, what's this one gonna do? It's gonna pull it that way, and this one's gonna pull it that way, because they're attracted.
But when you do the calculations on like the first one,
Yeah.
it like comes out to a negative number.
No, the first one comes out to be,
There's only one negative in there.
did I put the negative in the wrong place?
And then the second one, because there's now 2 negatives, would be positive, right? Is that right?
Yeah, I wanna go from 1 to 2, right? So 8.988 times 12 times 18 times I hat. Oh, that's right, that's 1 acting on 2. That should be negative, thank you.
Okay.
Yeah, 1 acting on 2 is gonna pull it this way.
Oh.
Right? Charge, this is positive, that's negative, this one's gonna get pulled that way, so it's negative. This one is a negative times a negative, it's positive. That's 2 acting on 1, right? Because they're going from charge 2 to charge 1, this direction. Okay, so you have to include the direction. All right, let's try one a little more interesting. What do you say?
So,
Go ahead.
would it always be that way? Like, would it always be that this one acting on this one would be this?
Equal and
direction?
opposite, yeah.
Okay.
They're, right, but they could be pushing each other if they're positive, if they're both positive, instead of attracting.
Yeah, that would, yeah. Okay, that would make sense.
Will we ever have them working in like the Y direction?
Yes, but oh, okay. All right, 2 small beads having opposite charges. Let's make this a little more interesting. Okay, here we go. So, 2 small beads having positive charges Q1, so charge 1 is 3Q, and Q2 is Q, are fixed at the opposite ends of a horizontal insulating rod of length D equals 1.5 meters. So that means the rod can't conduct any charge. The bead with charge Q1 is at the origin as shown in the figure. A third small charge bead is free to slide on the rod. So another rod that can get pushed. So here's the picture. All right, so we got Q1 here. Q1, a rod, Q2, Q1 isn't it Q?
3Q, I think it's
Which one's Q, 3Q? Q1?
Q. Yeah.
You're right. So this is 3Q. Q2 is Q. They're both positive. I think the distance between them L is 1.5 meters. A third small charged bead, so let's call this little bead here, and let's give it a charge Q sub naught. That's different than these Q's. A third charge is free to slide on the rod. At what position X is the third bead in equilibrium? So where can I put this such that it's got equal forces, right? What does that mean to be in equilibrium? What?
The sum of the forces.
Sum of the forces is 0. So I want the forces acting on that charge to equal 0, right? So I want the force of 1 on Q0 plus the force of 2 on Q0 to equal 0. Right? Does everybody interpret? See what I wrote? Can you interpret that? Charge 1 acting on Q0 plus charge 2 acting on Q0. Where is that thing in equilibrium? Let's do it from the X here. So this is X equal to 0. So what X is this in equilibrium? So now I gotta add 2 charges. So I gotta be a little more careful with the signs and the directions here.
What's the Q1 and the Q2 equal to?
Q1 is 3Q, Q2 is Q. We don't know what Q is. It's just Q. The charge is Q naught, that's the B. Let's see if we can find out where that charge is. And then we'll answer question B second. Let's do question A. We'll do 2 dimensions on Wednesday. Stick with 1 today. So you gotta set up Coulomb's law for each one and add them up, right? You don't forget direction. Keep forgetting my phone's over there.
Do we know the forces? Oh, yes.
We know it's Coulomb's force, right?
No, do we know not forces, sorry, the charges?
We don't know the charges. I think it'll cancel. So call it Q right now. Call one Q and the other 3Q. I think what's important is the ratio.
So Q1 is 3Q.
Yeah. Let's see if we can get the formula here before we solve for X. Let's see if we can figure out what the formula looks like. Give you a couple more minutes to do the formula. You got the formula, Jim? Just plug into this, right? K Q1 Q2 squared, the direction, plus K Q2 Q over squared.
I think I got it.
Someone else? Anybody else? Jared, do you think you got it?
How much, what's the length? Is it 1 point,
1.5.
is that the total length?
That's the total length.
Okay.
And you know me, I'll put numbers in at the end.
Yeah.
Give you another minute. that the formula you guys got? Does it look like that?
Except for, I would have a negative Q in the second half.
Both these charges are positive, so I kept them positive. I put the negative over here for the direction. Right, because it's a negative I direction. I mean, if you put it there, that's fine, but that's why
I had a
it.
negative Q over there,
Why do you have a negative Q?
because it's pushing like this.
Yeah, so that's what I have for my R hat.
Okay.
I mean, that's fine what you did, but you know what? There is not a negative charge, though. You see what I'm saying? But it's fine. Jared.
I just,
Oh.
I just, yeah, I just, instead of the.
Put it there, you put it
I
there.
subtract.
That's fine. That's fine. I'm just trying to be exact
Yeah.
in every step. Mary.
Two questions. So where does the 3 go in the second one? It's no longer 3Q. Why not? Oh, because it's
Because it's Q2.
okay.
Q2 is Q.
Q2 is just Q. And
That's
then-
fine.
So we're talking about the.
We did this one acting on this, and then this one acting on this.
Okay. And
This
then-
one's, they're both positive, so this one's gonna apply a force this way, and this one's gonna apply a force the other way. Right? Everybody see that?
Yeah.
Matthew, you see it?
Yeah, I was wondering why you did L minus X, but I was confused on what was acting on what.
That's L,
Yeah.
that's L minus X. This is X. So I need the distance squared. Okay, so now what do? I gotta factor stuff out and then set it equal to 0. Well, it is already set equal to 0. But I can factor stuff out to make this nice. Notice I can factor out a K and a Q and a Q naught and an I hat, right? Everybody see that? So I factor out a K, a Q and a Q naught. If I do that, I'm left with 3 over X squared minus 1 over L minus X squared times I hat equal to 0. Now I just factored out the stuff so I can look at what's 0. Right? K's not 0. Q and Q naught aren't 0. That means what? This has to be 0. Right, you guys see that? You with me, Sarah?
Can you say that again?
When I factored it out, then I have K times Q naught. None of these are 0.
Yeah.
So that means the thing in parentheses has to be 0. Right? So that means I can set that equal to that. 3 over X squared equals 1 over L minus X squared. Well, I can flip it and take the square root. That would be nice, right? I can write X squared over 3 is equal to L minus X squared over 1. Right? Just flip the fractions.
Yeah, sure.
You can do that, right?
I don't know.
When you like,
Your brain is crazy.
Yeah. 1/2 equals 2/4, right?
Just accept them.
Isn't that true?
Sure.
1/2 is 2/4? 2/4 is 1/2, right? And then I flip it, what does that tell me? 2 over 1 equals 4 over 2. You can flip a fraction. As long as you do, what you do on one side, you can do the other. Really what I'm doing is taking it and dividing it by 1.
Whatever you tell me about algebra is kind of acceptance.
Okay. I'm glad you believe me. Okay, so now we can cross multiply. So X squared equals 3 L minus X squared, right? Cross multiply, you guys remember that thing?
Yes.
Sarah? Danny? Okay. So take the square root. X equals the square root of 3 L minus X. Square root of 3L minus square root of 3X. Bring that over. X plus square root of 3X equals square root of 3 times L. Factor X out. 1 plus square root of 3 equals square root of 3L. X equals square root of 3L over 1 plus square root of 3. And L is what, 1.5? Square root of 3 times 1.5 divided by 1 plus square root of 3. Someone get that on the calculator. I bet if you're in math, you would leave it like that, right? Don't they leave square roots of 3s and things? What do you get? Sarah's typing.
0.95.
0.95 meters.
Oh, is there times 3 on there?
What was
Oh,
that?
No, never mind. Yeah, that's right.
0.95 meters. Nice job, Sarah. And is this equilibrium? What do they mean by that?
This can't be stable.
Yeah, is it stable, right?
What does that mean?
What does that mean?
Charges are not moving.
That means if I were to move it off the middle here, which way is it going to go? If I move it a little bit to the left, what's going to happen?
It goes to the right.
Because this force is going to get stronger, it's going to push it back to the right. Right now, I move it to the right, what's going to happen? This force is going to push it back to the middle. So this is a stable equilibrium, because the forces are pushing opposite, pushing to the middle. Right? It's kind of like the ball in a valley or on a hill. Right? If it's in a valley, what happens? Gravity keeps pushing it to the middle. But if you're on top of a hill, it's an equilibrium, but what happens if you move a little? Then you fall off, right? So this one's a stable equilibrium, because you can see the forces are pointing, right, against each other. Right? If the forces were kind of pulling, if this is pulling and pulling instead of pushing and pushing, then it would be unstable. All right? Does that make sense, everybody? I think if these were two negative charges here instead of positive, then it would be an unstable equilibrium. Because once you moved a little bit, you get sucked over. Because that one would get weaker, that one would get stronger. Does that make sense? This is a stable equilibrium. Well, I assumed it was a positive charge. If it was a negative charge, it would be unstable. But we assumed positive. Alright, we'll do 2 dimensions on Wednesday. Right, so we'll do X and Y. So then you have to really do some vector stuff. Today was just kind of positive, negative direction, right? So we'll do I's and J's. Work that out in detail. Alright, questions? Alright, we're moving on past heat, temperature. I know it's so sad to leave that behind. Entropy, engines. But you'll see it again.
Can I go?